is meant by an isotope? So, an isotope, well, you probably know this from chemistry, right? What do you say in chemistry?
I always get mixed up sometimes, but it's the same electrons, but it's a different neutron number.
Yeah. An isotope of an element is the element with a different number of neutrons, but the same proton number. That's what you're saying, isn't it?
Yeah. Can I change neutrons to neutrons as well?
Can you say what?
You can't say neutrons. Instead of neutrons. Different number of neutrons.
No, it needs to be neutrons, because you could have different nucleus number could mean a different proton number too.
Okay.
B. So, what is the nucleon number? What's the nucleon number?
It's the mass number, the neutrons plus
Yeah.
protons.
Okay. And then C, you have to fill in the blank 238U and then blank 90TH plus blank. So this is an alpha. So that means this here has to be 2, 3, 4, yeah? And this has to be 92. Is that okay, Chow? This is A9. Yeah? We can look at A10?
Yeah.
5 capacitors are used to store energy. Determine the capacitance of the circuit if they're connected in series. So in series they're like this. 1, 2, 3, 4, 5. So the formula is 1 over C equals 1 over 2 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus 1 over 2, which equals 1. So C equals 1 farad for part A. You look, it's okay, Joe?
Mm.
Part B, if they're like this in parallel. 1, oh, it's hard to draw. 1, 2, 3, 4. 1, 2, 3, 4, 5. You get the picture. So here the C equals 2 plus 2 plus 2 plus 2 plus 2. So that's equal to 10 farads. And then C, what is the maximum energy you can have? Okay, so which would store more energy, A or B? So you have to use B, because you get more. Okay, in the formula, do you remember, the energy is a half CV squared. So that would be 5 times 25 squared That's 5 times 625. That's 6250 over 2. What is it? 3125? Joules. Just gonna have a quick check of the marking scheme. I'm sure it's okay, but I'm just a bit curious.
V is 25.
I thought I said 25 in the question.
Yeah.
Oh yeah, of course, and I'm supposed to use 3 significant figures, so that'd be 3130 joules, which is 3.13 kilojoules. Great. Okay. Is that okay? Yeah. A? Yeah?
1 over 2 plus 1 over 2 plus 1 over 2.
Oh, sorry. It's not 1. It's not 1. Sorry. Thank you. It's 2.5. Yeah, sorry. Sorry.
I was confused there.
Yeah, sorry. Is this 0? This is 0.4? Is it? What is it? 1 over 2.5. 0.4?
Yeah.
It's 5 over 2. 2 over.
Yeah, 0.4.
Yeah.
I tell you, Chow, what I was thinking in my head, I was thinking 2 times 5 is 1. That's, I don't know why I was thinking that, so that's why I said 1. Okay. Continue. B1. A. In a race, runner A starts at rest and has an acceleration of 8 for the first 0.8 of a second. Okay, so 0 to 0.8, this is time in seconds, this is velocity in meters per second. So it goes like this, and this is 8, okay? Then travels at constant velocity for the remaining 100 meters. Okay. $100 meters. Okay, question 1. What's the distance here? They want the distance here. So, remember you can say rise over run equals 8. So if I call this, look here, if I call this V, I can say V over 0.8 equals 8. So V equals 6.4 meters per second. So that means the distance, which is a half the base by the height. What's that? 0.8 times 3.2.
2.56.
Okay. That is correct. Oh, ha. I've actually done part 2 first, which is to get the V.
I see.
So it means that's handy. So I've done part 2 first and then part 1.
We can do that, yes.
You can do that on the exam. I don't see any problem with that. So I've gotten 4 marks.
Is it okay if we do the exam like B3 first and then B2?
Yeah.
Okay.
doesn't matter, you can multiply either of them by a half. Yeah. The order is not important for multiplication.
It's just like only one of them will be half instead of both of them.
Yeah, only one of them needs to be halved. It doesn't matter which one actually. Can I continue? So the next part is they want the time here. So if you see, if that distance is 2.56, then it means that distance is 97.44. Is that right? That's right, isn't it?
Yeah.
If 100 minus 2.56, yeah? I think so. Is that right? 97.44, yeah? So, if you look here, the base multiplied by the height should equal 97.44. So, Andek, maybe if you just divide that there.
On 15.225.
So the total time is 15.225 plus 0.8, which equals, what's that, 16.025, which is equal to 16 seconds. Yeah. Do you need to move the projector? Oh, japers. And maybe you can move it a bit to the left so it's right at the edge. Can you get it right up to the edge of the screen? Yeah. Bit more? Push it all the way. Okay, now release. Yeah, that's better. No, good. Okay. Yeah. Yeah. You cold?
Cold. I'm weak.
Weak. Oh, it opened again. It's open. Yeah. You didn't quite close it. Give it a good push. Is it broken?
Or just close this one, the white door.
Yeah, close the white door as well. Yeah. That'll help. Okay. Right. Can we go to the next part? Yeah. So, B. Runner B has an acceleration of 6. So that's a 6 there, meters per second squared. For the first 1.1 second. Okay. It's still 100 meters. Right. Can we calculate here velocity and time? So if I call this here v, I have v over 1.1 equals 6. So v equals 6.6. 6.6 meters per second. Okay? What's this distance? It would be a half 1.1 times 6.6. What's that, please, Andek? Yeah, it's okay. It's like about
3.63.
3.63, is it?
Yeah.
So then that means this distance here is 96.37 meters?
Yeah.
I think so.
Yeah.
So if I want this time here, I can say time multiplied by 6.6 equals 96.37. So that divided by that is, when you're ready, 14. 6015.
Yeah.
So that means that the total time will be 1.1 plus that, so that's 15.7015, which equals 15.7 seconds. So, who will win the race? Who will be faster, A or B? What was the time for A? A was 16, and B is 15.7. So who will win the race?
B.
Yeah. Runner B will win the race.
Sorry.
Yeah. Shall we go on to C?
Yeah.
Chow?
Yep.
You sure? Okay. C. In an experiment, a U-shaped tube is filled with water, so it looks like this. And the water is allowed to oscillate back and forth between two sides of the tube. The oscillation of the water behaves according to simple harmonic motion. It's observed that 10 oscillations take 16 seconds. Okay, so if you look here, what's happening is the water is moving up and down. So maybe it goes up here and then it goes down here, and then later it goes up here and it goes down here. So it's oscillating up and down. And the question says it's 10 oscillations in 16 seconds. Question 1, what's the frequency? Okay, so the frequency equals 1 over time, and the time equals 16 divided by 10, which is 1.6. So that's 1 over 1.6, which is something. 10 over 16, 0.625, is it? 0.625 hertz?
Yeah.
Nice. Part 2. If you change the amplitude, what happens to the frequency? Any ideas? Yeah?
No, because it goes twice, I think.
Yeah, for this one here, the frequency is unchanged.
Stays the same.
Yeah. Ah, now maybe you remember this word. So what do you call it when amplitude decreases? Do you remember what that's called? In the simple harmonic motion lesson, when amplitude decreases over time. You know, the graph like this.
Yeah.
Do you remember what that's called? Remember? its name? Begins with a D. Dampen. Do you remember that, or it's gone?
It's gone.
It's gone. Part 4. They tell you the amplitude is 0.05 and they want the acceleration. Okay? Yeah? So, what formula could we use? We could use the formula A equals A minus A omega squared. So the maximum acceleration would equal A omega squared, which would equal 0.05. Oh, and omega is 2 pi over t.
That's the general form of omega squared.
Yeah, omega is 2 pi over t. Alright, so if you just bash that in and when you're ready. Say again, sorry? 771 meters per second squared. Very good, okay.
Sorry.
Yeah.
Why A equals minus A omega squared?
The minus is just to remind us that if this is moving to the right, the force is to the left. So this is just to tell us that it's going opposite. So when the x is positive, the acceleration is negative. That's all. Okay, can I scroll down? So the last part here is they want you to describe what happens to the energy. Okay, so if you look here, let's imagine it starts off like this. The water's up here and the water's down here. So it's like this here. So it's at rest. What will happen? What energy does this have? This has potential energy because it's like lifted. What will happen? Then the potential energy turns into kinetic energy because when this falls, it gets faster. So it turns into kinetic energy. But then what happens? Well, then it rises here. So it'll be up here and then it'll be down here, like that. So then the kinetic energy turns back to potential energy and it repeats. Okay, that's all they wanted you to say there. to you?
Alcohol.
Again? You seem to wake up late every Tuesday morning. So I want to know what you do on Monday night. Working? Gaming? Netflix? YouTube? Twitter? What happens? Game of Thrones? Okay.
Understand.
Is Game of Thrones released every Monday or something?
Monday midnight.
Aha! Now it all makes sense. Okay. Continuing. B2 now? Did you do this one, Andak, in the exam, B2?
Oh,
Did you do it?
yeah, I did.
Yeah. Chow, did you do B2?
No.
No, okay. And Matt, do you remember if you did B2 with the ropes?
Yes.
Yeah. In manufacturing a climbing rope, a number of samples are being considered. Which of these ropes would support the greatest weight before breaking? Okay, so I don't know if you remember this, but which word here? Tensile, stiffness, or diameter? Which word do we care about if we want to know when it will break? Well, it's not diameter, okay, because diameter means this. So it's not that. And it's not stiffness either, because stiffness means the K. It's tensile strength. This means the limit when it will break. So if you look at the three ropes, A, B, C, which is the strongest, A, B, or C? Rope A breaks at 1500 newtons. Okay. Something not quite enough. Hang on. Just a second, I'm just checking something here. Okay, I'm just wondering what you're thinking for the next part. Which of the three ropes... if the climber were to fall the same distance on each of these ropes, which would produce the smallest deceleration? So, what happens here is you have your climber, he's on the rope, and he falls a distance. So, we'll say he falls a distance, I don't know, L, or whatever it is. Okay, doesn't matter. As he falls, there's two forces, one up and one down. His weight, and then this force here from Hooke's law, which is K delta X. Okay? So, which would be bigger? The top or the bottom? Which force is bigger? Well, if I draw this a bit straighter, I think it's the top one, because he's slowing down as he falls. So, F would equal K delta X minus W, which is mg. and F is ma, which equals k delta x minus mg. So the A is k delta x minus mg over m. Okay, let me think. So, the question is, the only thing you can change here is k. This is the same. His mass is the same. G is the same, and his mass is the same. So if the only thing you can change is k, and they want the A to be the smallest, you want to make that a minimum. This means his fall is smooth. Which rope should you pick, A, B, or C? If you want to have the smallest A, it means you should have the smallest K. Which rope should you pick?
Rope C.
Rope C. Yeah. 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 Okay. 3. What is the stress? Right, do you remember the formula for stress? Stress is force over area. And they give you the force, it's 600.
Isn't it pressure?
It's the same formula as pressure, yeah. 600 over pi r squared. What's the r here?
It should be half diameter.
Yeah, which rope are we looking at? Rope C. So that's 4 millimeters, yeah? Okay, when you're ready, Andek or anybody, you can give me the answer here. What you got, Andek?
119. Is it big enough?
Yeah, they usually are.
1193662.73.
Like this?
Yeah.
So that's 119,000,000 times 10 to the 5 pascals. Are you sure? Oh no, it's right. It's right. Yeah, it's right. It's right. Okay. 4. Now they want to know the extension. The extension. So you have to use this formula. F equals K delta X. So delta X equals F over K. The F is 600 and the K for rope C is, what is it? 1.5 or 1,500 for rope C, isn't it?
Yeah.
Right, so what's that? So
0.4.
okay. 5. Sketch the graphs where on the y-axis you put force in newtons and on the x-axis you put extension in meters. So look, if you look at this formula, if F is on the y-axis and delta x is on the x-axis, what does the K represent?
The constant slope.
The slope, the gradient, yeah. So look at the three ropes. Which has the biggest slope then?
Row B.
Yeah, and then?
Followed by A.
Yeah, so BAC. So the graphs look like this. Oh, do we have to put in the tensile as well? Well, we'll just draw it like this. B, A, C. Which rope will break first? Which rope will break first? C. And then? And then? B. And then the last rope to break? A. So CBA. So then what you need to do to finish this is C will break first. So it breaks and then it goes off there. Then A breaks next.
A.
Oh, sorry.
Oh.
Thanks. Then B breaks next. So after C, it breaks. And then the last one to break is A. Like that. So, do you remember what those points are called? Do you remember what those points are called where it breaks? Tensile strength is the force. Oh, sorry, my graph is wrong. Sorry. It's too small. I need to draw it bigger. Okay. Extension in meters and force in newtons. Okay, let's just draw that again. What's the steepest one? It's BAC. Okay. BAC. Okay. Now, who breaks first? C breaks first. So what I'll do is I'll say this is where C breaks when it gets this much force. Okay, who breaks next?
A. Oh, no, B.
This is where C will break, and then B, is it?
Yeah.
Yeah, and then lastly, A. That's where A will break. So let me try and make. B goes up, and then when it gets to this amount of force, it breaks. And then C will break here, and then A will break here. Okay, that's better. No, just it says sketch. Alright, and lastly, I asked you a moment ago, what are these points called where they break? Do you remember what they're called? Elastic? No. No, you want the noun. Elastic limit. I guess so. You can stretch B the least. You can stretch A the most. Yes. Yeah. There's kind of a hard question for 4 marks, That's kind of hard. Okay, can we do the next part? Find the modulus, Young's modulus. So, what's the formula for Young's modulus? It's stress over strain. Stress is force over area, and strain is extension over length. But, do they mean rope A, I wonder, or do they mean to say rope C? Because we've been working with rope C all this time. No, it is rope A. Okay, fine. Right, let's see. What information do we know? Do we know the area? Yes. Do we know the natural length? We do, yes, because they're all 30 meters. Good. Do we know the extension? Do we? I don't think we do. We know the extension for rope C, but we don't know it for rope A. So do we know this? Huh? Well, we can calculate it, but do we know the F? Do we know the force on rope A? No? No. The tensile strength is the limit. So look, here's the problem. We don't know this and we don't know this. That's the problem. Okay, but that's easily fixed. Watch. If you remember that F equals K delta X, then this becomes K delta X over A over delta X over L. Now what happens here? You see, they cancel, and now you're left with K over A over 1 over L, which is equal to LK over A. Now, do you know the natural length? Yes, it's 30 meters. Do you know the K? Yes, it's 1680. And do you know the area? Yes, you can work it out. So the answer will be 30 times 1680 over pi. And what's the diameter? 5. Okay, so what is that, please? Yeah. How's that?
Yeah.
Yeah. Got that? What you get?
6471273.0.
So what's the first 3 digits?
642.
642. And let's just check. 10 to the 8 then. Was it? Probably, yeah. Okay, B. Okay, B. So you have a projectile here, This is 35 degrees. This is 18 meters per second. And they want to know, well, basically, the first thing we want to do is calculate these two. So this is 18 cos 35, and this is 18 sine 35. What are those two numbers? So yeah. Yeah. 18 cos 35? And you can give me 18 sine 35, yeah man? 14.7, yeah, meters per second. And 10.3 meters per second. Okay, part 2. What is the maximum vertical height? So that's when the ball gets up to here. So U is 10.3, V is 0, A is minus 9.81, T we don't know, S is what we want. So what would be the best formula here? I think it would be V squared equals U squared plus 2AS. So that's 0 equals 10.3 squared minus 19.62 S. So S is 10.3 squared over 19.62. You can tell me that when you're ready.
Wow.
5.41. It really annoys me that they're not consistent in the marking scheme. So the reason that, so in the marking scheme they don't use 10.3, they use 10.32. But for the previous question, I don't like when they do that. Anyways, part 3. So for part 3, we're looking at the ball going all the way to the end. Okay? So let's first get the time. U is 10.3. V is, don't know. A is minus 9.81. T, we don't know. And S, we do know it's 0. And if I use the formula S equals UT plus a half AT squared, I get 0 equals 10.3 T minus minus 4.905 T squared. So T is 4.905. No. 10.3 over 4.905. And so the range would be the distance horizontally. That's 14.7 times 10.3 over 4.905. So that's the answer when you have it.
13.9.
Yeah.
Sorry.
Yeah.
It's T squared.
Yeah, so what I did was I divided by T. Okay. Got that? Yep. Shall we look now at the next question, which is B3? Yeah. Who did B3? You did B3. Did you do it, Andek?
No.
Chow? No? Did you do B3? No. A person notices that his or her skin feels colder when it is wet compared to when it is dry, even though the air is at the same temperature. Explain this effect with reference to latent heat of vaporization of water. So, here's their skin, and here's some water on it. And then here's their skin, and it has no water on it. And the question is, why do they feel colder when there's water on their skin? So you can think of it like sweat nearly. So here's the heat, and here's the heat. And they feel colder when there's water on them. Even though maybe the temperature is the same. Now, let's say, for example, it's 30 Celsius outside. So why does the water here make them cooler? Well, what happens is the water vaporizes. And as it vaporizes, it needs to take heat energy from the skin so that it can turn into steam. Okay, so what happens is the energy required to have vaporization is taken from the surrounding skin. So write something like that. Yeah, that'll do. This is why we sweat. We sweat because the water, when it turns into steam, it takes heat from our body away.
So the water vaporizes into the skin and the energy required to take
water vaporizes on the skin. Yeah.
And then followed by the energy is required.
It takes the energy from the skin, yeah.
The word before skin.
Sorry, surrounding. Surrounding. Sorry, surrounding. Can I do part 2? Matt? It's okay, part 2, yeah? What's the energy to convert 20 grams of water from steam to water? Okay, so can I scroll down?
Yeah.
So look, what you have is you have 20 grams of a 100 Celsius steam, and this steam cools down back to liquid water, and it's still 20 grams, and it's still 100 Celsius. So it lost energy, and the formula is equal to just ml. So the answer here is 0.02 times 2256000. Okay, what's that? 45,120
120.
joules. So that's 5 kilojoules. Yep. Okay, part 3. It then says it goes from 100 down to 80. So what formula do I need now? I need this one, mc delta theta. So that's 0.02, 4184, and 20. So what is that now? Say again? 1673. So that's 1.67 kilojoules, yeah? So the question is, what's the total Q? So the total Q would be 45 plus 1.67 kilojoules. So what's that? 46.7 kilojoules. Huh? Right. Did I add something wrong? 46 point. Hang on, maybe I'm doing something wrong in my head here. What is this if we add them? 46.67 kilojoules, isn't it? So that is 46.7 kilojoules. Now what's annoying me about the guy who's writing the answers here is, you see here the answer is 1.67, and he says the answer is,
Sorry, the 4184 is in joules?
huh?
The 4184 in the...
4184 is joules, yeah. Yeah. Well, hang on. What? Oh, I'm sorry. No, this is my mistake. I'm sorry. This is not the final answer. So because it's not the final answer, I should use 4 significant figures. So that's 1.673. But that doesn't change my answer here, does it? Oh, guys. I said the answer is 45. It's not 45. What is it? It's 45.1. Because there was a 1 there. So that's 45.1. So 45.1 plus 1.673. What's that? Can you tell me, calculate, please? There we go. That's the answer. 46.8. Lose a mark, yeah.
Really?
Yeah, because it was my mistake, Matt. Here, it wasn't 45. It was 45.1.
Even the steps are correct. The answer is 0.1 difference 0.
Well, just the last mark. So, for example, this question was 3 marks. You would get 2 marks, or I would get 2 marks. Actually, it's worse than that, because here you would lose 1 mark for making the mistake here. So that would be 1 out of 2, and then this one here would have been 2 out of 3.
If I write 46.77
For which part?
for the last answer, that should work.
You also lose 1 mark.
Is it because it's not the significant figure?
It's not 3 significant figures, yeah.
So everyone else has to be 3 significant.
And calculations have to be, I think we said 4 or more. I know, it's terrible. I really don't like it, Matt. This is not my choice. This is just me following the instructions of who makes the exam. Yeah. So you just want to be careful. Okay. Right, next part. Sketch a graph of temperature against time for solid to gas. Okay, so look. Here's the time. Here's the temperature. And they say from solid to gas. So for example, if it's ice, we know the temperature should be here, right? If it's ice, because it's less than 0. And as the time goes by, what happens to the ice? It warms up. Yeah. Warms up. And then, when it hits 0, what happens? It melts. So it keeps the temperature the same for a little bit. And then, starts to warm up again. Then, it hits 100. And then what happens? Turns to steam. And then it starts to warm up again. Okay? And they want you to mark where the melting is. So this is the melting. And then here is the vaporization. Yep. Yep.
The steam, the vaporization has to be longer than.
It is longer, but when I look at the marking scheme, he doesn't say it has to be longer. He just says you need to have 3 straight lines that are positive slope. So that's 1, 2, 3. You need to have 2 horizontal lines, 1, 2. And you need to mark where melting and vaporization is, here and here. So I can see when I check my answer, I did get all 4 marks, so this is fine. In fact, he doesn't even say, I marked 0 and 100 here, but I can see in his answer, he didn't even bother to say that you need to write 0 and 100. Now you should, but it doesn't seem to be necessary. Okay, continue. Yeah? Part C? Okay. C. Oh, an experiment is arranged to determine the specific heat capacity of a material. A block of the material of mass 3 kilograms is placed in hot water bath at 90 Celsius for a number of hours. It's then transferred into a known mass of water initially at 15. Okay, so look, this guy is at 90. And then what you do is you put it into some water. And the water is at 15. So the first question is, why do you heat this at 90 for so long? Yeah, what's the word? You're not optimum. So why did you heat this at 90 for so long? Yeah, give me a sentence, Matt, with a verb. Yes, that'll do fine. Yeah. So you want to say you want to make sure all of the 3 kilograms has reached 90 Celsius, and not just the outside, because you know, for example, if this is 90 Celsius, maybe it's only 90 on the outside, but it might be, you know, 50 on the inside. So you heat it up for a long time to make sure it's all 90, even on the inside. You know this when you cook food, right? When you cook chicken, it might be cooked on the outside, but not on the inside. So this is why you do it for a few hours, if you cook chicken. Well, depends how big the chicken is. Have you cooked chicken?
10 minutes.
Well, it's a small chicken, like piece of chicken.
Okay. The nugget, fried nugget. Something like that.
You could fry a small piece of chicken in 10 minutes, yeah. Part 2. Describe the transfer of energy taking place during this procedure. Okay, so when you heat this at 90 Celsius, they want to know how the energy is being transferred. For the whole process. Yeah, so we want to describe the whole process. So the whole process says heat energy flows into the 3 kilogram mass until it reaches thermal equilibrium of 90 Celsius. Then it is placed in water of 15 Celsius. And then what happens to the energy? And heat energy will flow from the 3 kilogram mass into the water until thermal equilibrium is reached. Oh, my hand. i.e. same temperature. Goodness sake, all that for 3 marks. I don't know. The energy flows into the 3 kilogram mass until it reaches thermal equilibrium of 90 Celsius. Then it is placed in water at 15 Celsius and heat energy will flow from the 3 kilogram mass into the water until thermal equilibrium is reached, i.e. same temperature. Any chance you wrote all of that, Matt?
I wrote the mass drop the heat energy from the 90 Celsius into the 15 degrees Celsius water.
I don't think that's quite enough. Alright, next part. Next part. So they tell you that the water, you have 5 kilograms. Yeah? And they also tell you that the temperature increased to 40 Celsius. Right? And they want you to calculate how much energy it got. So the formula is delta Q equals MC delta theta. What's the M here? What's the M? 5. The C, 4184. And the delta theta? What's the delta theta? Come on, what's the delta theta? 25. Right, so you can give me the energy here. $523,000 kilojoules. Okay. And finally, they want to know what is the specific heat capacity of the material. So, where did the water get its energy from? It got it from the block. So the energy that was lost by the block will equal the energy that was gained by the water, which we know is 523. Now, Mark, what was after the 523? Was it a 0? 0, 0, 0? Okay. And this here is M. What's the mass of the block? 3. C, we don't know. We want to know it. And the delta theta, it went from 90 to 40. So what's that? 50, isn't it? So cancel, cancel, and divide by 150, and we have our answer. Oh, that's nice for 3 marks. So 3.49 kilojoules per kilogram Kelvin. Now, Matt, you were asking me earlier about, what happens if you make the mistake, but you do it right and all that. So sometimes in the question, I don't know why, but sometimes they say, if the student made the mistake in part previous, then they don't lose the mark in the next part, even though the answer will be wrong. Okay, so for example, in this question here, it says you can still give them full marks if they got this answer wrong and brought it down. You can still get full marks. It doesn't matter how wrong, it could be completely wrong, but you can still get full marks here if you use this answer that was wrong. But the thing that annoys me is this is only true for some of the questions. Which ones, I don't know, it's just random. So for example, in this question, you could do that. Whereas, if I look at question 1, like a good example was earlier, you see here in this question here, to get this answer, you needed to use this answer, and this answer came from the previous part. Okay? For this one, no. If you make a mistake here, then it's also wrong here. I don't understand. It's random. It seems like they just decide for some questions that you can make a mistake and it's okay for the next part, but then for other questions it's not. Why they do this, I don't know. They're not consistent, which really annoys me. But oh well. I guess it's you that's doing the exam, not me, so it's your problem, not my problem. Okay. Question 4 now. An experiment is carried out to investigate the speed of sound in different media. A narrow tube is used. It's closed at one end and open at the other end, and there's a microphone for measuring the volume of sound. A speaker is positioned nearby, and a stationary wave is produced in the tube, and the tube initially contains air. A part 1. Sketch a diagram to show the amplitude of particles displaced in the tube for the fundamental frequency with any nodes or anti-nodes labeled. So, okay, here's your tube. And you have a standing wave in it, and the wave looks like this. Okay? And it's vibrating up and down like that. So this part here is called the antinode, and this part here is called the node. And the way I explained this is, if you imagine that you have some sand on the ground, then what would happen is all the sand would build up here and then would kind of be flat here. So I think, I don't even think I need to draw that much. I think I could just draw this. Let me check the marking scheme. Yep. enough. Okay, 2. The frequency is 165 hertz. The length of the tube is 500 millimeters. What's the wavelength? Okay. What's a first question for 2? Yeah, okay, what's the wavelength here? What's the wavelength? How big is the wave here? Well, how much of the wave do I have? Do I have all of the wave? Yeah. I have a quarter of it, don't I? So that means this would be 2,000 millimeters, which is 2 meters. Part 3, what's the V? Do you remember the formula for V? Try again? Well, lambda F. Okay, 4. The air is replaced with gas. And the frequency is now 200. So I've noticed with this guy that there's 2 things he likes to do to stretch a question out. Do you remember what one of them was? Definition true, but something else he likes to do. So do you remember I was saying that he likes to stretch the question out because sometimes he would say then, what would happen if you half the blah blah blah, or if you double the blah blah blah. Okay. It seems another thing he likes to have you do is to do everything again, but with a different number. So we have to repeat everything with a different frequency. The frequency is 200. So let's recalculate everything. V equals lambda F. What's the lambda? It's still 2 times 200.
So what is 200 come from?
They tell us that in the question, part 4. 200 hertz.
We get the wrong question, sorry.
Oh. Looking at the... Oh my goodness, that's... Yeah, just 400, that's the answer. Fine, okay, that's fine, alright. V. 5. They want to know what's the length for the next harmonic. So here's the first harmonic. That's like this. And that we said was 500 millimeters. And they increase the length until you get the next harmonic, which would happen when, let's see, node, antinode, node, antinode. This is the next one, because it has to finish on an antinode. So how much bigger is this compared to this? This is 3 times bigger, isn't it? If you picture it like this, there's 1/4 of the wave. 1/4, 1/2, 3/4. So I think the answer is 1500 millimeters. Let me check. I am correct. Yeah, so far I think this is pretty normal, yeah. You don't like it?
It's easier than others.
Well, it depends who writes the exam, you know. But I usually think the wave questions aren't so bad. Let's have a look at the B part now. A laser produces a beam of monochromatic light of wavelength 1.06 micrometers. And the wavelength... Oh, okay. Part 1. What does the word monochromatic mean? Anyone know? One? Mono means one. Good. So it's definitely one. What's chromatic? You might not know this word in English. No? Do you know the word chromacy, chromatic, chrome? You know what it means? It means color.
Yeah.
So monochromatic means one color. 2. What is the energy per photon? So the formula is equal to HF. Do we know the F? We don't. But we can calculate it because it's C over lambda. So that's H times C over 1.06 times 10 to the minus 6. So I'll let you calculate that, please. They're constants. They're in the formula book. Okay.
Will we give the formula book?
Of course.
Good.
Right. What is the power of the laser? So the power would be the energy from each photon multiplied by how many photons you have, which is 1.26 times 10 to the 16. So what's that, please? If you were to multiply them, it should be pretty small.
Is this a formula?
No, it's not. I want to call it common sense. What I mean, Matt, is you've worked out the energy for one photon and they've told you how many photons you have, so
For one.
everything's per second, yeah.
One 2.37 times 10 to the power minus 3.
So that's 2.37 milliwatts. Now, they say, Matt, the answer is 2.36.
It says 2.368.
Yeah.
So they made a mistake. Yes, they made a mistake because on the previous line they did say 1.88. That's what we have, isn't it? And they did say 1.26. So it's definitely 2.37. So this is definitely their mistake. So even they can get their significant figures wrong. Okay, next. Part 4. So you have the laser and it shines through a double slit and it makes, do you remember here the pattern on the screen? We know that the X is 4.24 times 10 to the minus 3. And the x, if you remember, is the distance between the fringes. They also tell us this distance here. They say it's 2 meters. What else did they tell us? Oh, we know the lambda, because we have that earlier. It's 1.06 times 10 to the minus 6 meters. And their question is, what is the d here? So the formula was x, is it x equals lambda d over d, is that right? Do I have the right formula? Yeah, I do.
What is the big E?
2 meters, they say in the question. Is it okay, Matt? So, d equals lambda d over x, which is 1.06 times 10 to the minus 6 times 2 over 4.24 times 10 to the minus 3. What do we get there? So meters. And finally, last 2 parts, V. So this is a classic question by him. He wants to know what would happen if the lambda is smaller. What would happen to the x? What happens to the x if the lambda is smaller? Come on, look. What would happen to the x if the lambda is smaller? Yeah, good. It's only 1 mark. Okay, and then the last part, if the slits are moved further apart, so if the d is bigger, then what happens to the x? Great. Ah, good. We only have 1 question left to do, and then we can go back to version 1. Okay. Yeah? You have that written down? Yeah. Right. What class have you got next? Okay. Test? Nice. So now we don't have Siba or Kim. Do you think they'll watch this later?
We should send a message to them.
Let me tell you what I really think of Siba and Kim.